The following presentation is on understanding vectors algebraically. We'll just jump into some examples. So this first problem here says, write and illustrate vectors in component form and in unit vector form. Well, if my vector starts at this particular point and ends, we see that the head of that vector is here. We're moving 1, 2, 3, 4, 5, 6, 7 units to the right, so positive 7, and 1, 2, 3 units up, so 3. This is called component form, and it's called component form because the vector is written in the xy components. Now, if we also want to write in unit vector form, this would be 7i plus 3j. The next one, it looks like we are moving 1, 2, 3, 4, 5, 6 units to the left, so that's negative 6, and 0 spaces up or down. So our component form looks like this. Our unit vector form is negative 6i plus 0j, or just negative 6i is fine as well. The next one, we're moving to the right, 2 units to the right, so that would be positive 2. And then 1, 2, 3, 4, 5 units down, so negative 5. Component form, and then unit vector form. So as the instructions say, I need to write it in both. The next one, we are moving 0 spaces left to right, so in component form we have 0 and 1, 2, 3, 4, 5, 6 units up. And then unit vector form would be 0i plus 6j, or just 6j. That would be fine as well. The next one, 1, 2, 3, 4, 5, 6 units to the left, so negative 6, and 1, 2, 3 units up, so component form, and then unit vector form. The next one, 1, 2, 3, 4, 5, so negative 5 units to the left, and then 1, 2, 3, 4, 5 units down, negative 5. So this is component form, and then unit vector form. Write each vector in unit vector form and illustrate it using, well, I don't think that I really need to do this. So this is pretty, I think that the last problem was pretty self-explanatory, but if we want to write this component form as 3, 4 into unit vector form, it would just be 3i plus 4j. And then they want us to write or illustrate using an arrow diagram. Well, that would be, so we'd have 1, 2, 3 units to the right, and 1, 2, 3, 4 units up. So we're looking at something like this. So I don't really feel I'm going to skip the rest if that's okay. The next one, let's look at this problem. It says, find in component form and unit vector form. I'm trying to find this vector from B to A. From B to A, so our vector is going in this direction here, which is going to be 1, 2, 3, 4 units to the left, so negative 4, and 1 unit down, negative 1. So that would be our component form, and then our unit vector form would be negative 4i minus j. I'm not going to do all of these. Let's skip to E. From C to A, from C to A, we're looking at this vector here. 1, 2, 3, 3 units to the left, so negative 3, and then positive 1, 2, 3, 4 units up, so that would be, so negative 3, 4, or in unit vector form, negative 3i plus 4j. Let's move down. It says, write in component form and illustrate using a directed line segment. If I want to write this in component form, this would be 1, 2, this would be negative 1, 3, this would be 0, negative 5, and this one would be 4, negative 2. And if we want to illustrate with a directed line segment, this negative 1 would be 1 to the left and 3 up, so it would look something like this. This one would just be directly down. This one here would be 3 to the right, 4 to the right, 1, 2, 3, 4, and 2 down, 1, 2. So it's going to look something like this. Write the 0 vector. It says write the 0 vector 0 in component form. All right, well, in component form, we would just have this. So our component form has some x value and a corresponding y value. This is how you write in component form, so this would be our 0 vector. Now here it says find the magnitude. Find the magnitude of these vectors. So I have the magnitude. So if I have a vector that is 3 units, 1, 2, 3 units to the right, and 1, 2, 3, 4 units up, we have this vector. We can construct a right triangle with a base of 3 and a height of 4. So to figure out this length here, this magnitude, we could just use the Pythagorean theorem of 3 squared plus 4 squared equals our magnitude squared. 3 squared is 9 plus 4 squared is 16 equals our magnitude squared. 9 plus 16 is 25. 25 equals magnitude squared. We take the square root of both sides, and our magnitude is going to be 5 units. Our magnitude, or the size of our vector, is 5 units. We do the same thing with all of these. C, it looks like I'm moving 2 units, 2 units to the right, and no spaces up or down. So we can, just by inspection, we can see that our magnitude is going to be 2. But if you're so compelled, we can use the Pythagorean theorem of 0 squared plus 2 squared equals our magnitude squared. 0 squared is 0 plus 4 squared, if 2 squared is 4, equals our magnitude squared. We take the square root of both sides. The square root of 4 equals 2. I don't mean to say that it doesn't equal. Just getting a little bit sloppy. So here we have -2, all of -2 squared plus 2 squared, all under a square root. That's going to give me 4. 4 plus 4 would be 8. So we're looking at the square root of 8. And if you want to clean this up, we can do a factor tree. 4 times 2 gives me 8, and 2 times 2 gives me 4. So we have a group of 2's that can be pulled out of the square root, which would give me 2 times the square root of 2. This one here, the magnitude, 0 spaces left, right, and 3 spaces down. 1, 2, 3. So our magnitude is going to just be 3. I think it might be helpful to do this one. I was going to skip it, but because of this negative, it just seems like a common mistake that students make. They'll say 3 squared plus -4 squared, and then all under the square root. And the problem with this is that -4 squared is not the same thing as -4 in parentheses squared. -4 squared is -4 times 4, which is -16, which is not the same thing as -4 times -4, which is a positive 16. These are not the same thing. So we just need to make sure that we use parentheses here to indicate that we are going to square all of this b value. So 3 squared, that's 9, plus 4, -4 squared, which is -4 times -4, that's 16. I end up with 9 plus 16, which is 25. I have the square root of 25, which is just going to be 5. And by looking at these two vectors, we would expect that if I have a vector that goes 3 to the right and 4 up, that should be a vector that's the same size as a vector that goes 4 to the left, 1, 2, 3, 4, and 3 up, 1, 2, 3. This vector should be the same size as this other vector over here. So we can continue, and it says find the length of this vector I plus j. That means we have a vector that goes 1 unit to the right and 1 unit up. We're looking at this little vector here. So we're going to find the magnitude. That is 1 squared plus 1 squared, all under the square root. 1 squared is 1 plus 1 squared is 1, so I have 1 plus 1, which is 2. I have the square root of 2. So I think you basically have the same idea, or you have a good idea of how to find the magnitude or the length. It's the same concept. We're just finding the size of the vector. Number 3 says, which of the following are unit vectors? A unit vector is a vector with a magnitude of 1. A unit vector is a vector with a magnitude of 1. So we can see that this one has a magnitude of 1, just going up 1. We should be able to recognize this from our unit circle as a 45-degree angle, so this would be negative. Becomes the same thing as the square root of 2 over 2, if you recall. So we have the square root of 2 over 2. So this is going to be, from our unit circle, we should remember that this is also a unit circle. So this one is yes, this one is yes. By inspection, I am not sure. So what we could do is we have 2/3 plus 1/3. It looks like if we have 2/3 in one direction and 1/3 up, it looks like it should be 1. But let's use our magnitude. And so we have 2/3 squared plus 1/3 squared, all under the square root. Does this equal 1? So I have 2/3 squared, which is going to give me 4/9. And then I have 1/3 squared, which is going to give me 1/3 times 1/3, which is 1/9. And then we're going to, take so we have the square root of 4/9 plus 1/9, that's going to give us 5/9. So the square root of 5/9, or the square root of 5 over 3. So it looks to me that this is not going to have a size, it does not have a magnitude of 1, so this one is no. These, yes, yes, and no. So we do the same thing, just make sure we plug these in, of our a squared plus our b squared equals our magnitude squared, and then take the square root and see if it equals 1. If it equals 1, it is a unit vector. If it doesn't equal 1, it is not a unit vector. Let's continue. It says here, find k for a unit vector. Recall again that a unit vector is a vector with a magnitude of 1. So if I have a vector 0k, then k has to be 1, because our vector is going no spaces left or right, and then we're going 1 up. But it is also true that k could be -1. We could also be going in the opposite direction. So there's 2 values here. Here, there are 2 values as well. I'm going to use our formula, even though it's obvious that k is either 1 or -1. Let's use our formula. We have, if it's a unit vector, then we have k squared plus 0 squared, all under the square root, and that equals 1. All right, so we need to find k. We're going to take the square root of both sides, and so the square root squared, they undo each other, and I'm left with k squared plus 0 squared equals 1. But 0 squared, of course, is 0, so I'm left with just k squared equals 1. So I take the square root of both sides, remembering that this is plus or minus, remembering to put plus or minus anytime I use a square root. So then that gives me k equals plus or minus 1, which that's what I thought it would be anyway. So we do the same thing with this value. We plug k in for a squared plus b squared. That's going to be 1. I'll do this one. I'm just running out of spaces. Yeah, let me do the last 2, just because I'll have more space for this. So I have k squared plus k squared, all under the square root, and this should equal 1. Take this. I'm going to square both sides. That's going to give me k squared plus k squared equals 1 squared, which is just 1. K squared plus k squared is 2k squared equals 1. I'm going to divide both sides by 2. That's going to give me k squared equals 1/2. Take the square root of both sides. It gives me k equals plus or minus the square root of 1 over 2, or k equals plus or minus 1 over the square root of 2, which is basically what we had up here. So this is basically the plus or minus the square root of 2 over 2. Right, the last one. This is not the last. Actually, I'm going to continue doing a couple more. So here we have 1/2 squared plus k squared, all under the square root. And if this is a unit vector, it should equal 1. All right, so I'm going to square both sides. That's going to give me 1/2 squared plus k squared equals 1 squared, which is 1. And then we have 1/2 squared is going to give me 1/4 plus k squared equals, and it looks like I'm going to have to subtract 1/4 from both sides, so I'm going to make this one 4/4. I'll subtract 1/4 from both sides. That gives me k squared equals 3/4, and then take the square root. K equals plus or minus the square root of 3/4, or k equals plus or minus the square root of 3 over 2. So there's two values for that particular problem because we know that the vector can go in two different directions. Specifically our y value. So our up, down, one vector, the vector is going to always go to the right by a half, but it could go up or down depending on whether k is positive or negative. All right, let's look at number 5. It says, given that our vector is 8p and the magnitude of our vector is the square root of 73 units, and I want to find the possible values of p. All right, so that means that I have 8 squared plus p squared, and then the magnitude, which is the square root of all this, is going to equal the square root of 73. I'm going to square both sides. That gives me 8 squared plus p squared equals 73. 8 squared is 64, so I'm going to subtract 64 from both sides. So I have p squared equals 64. I'm going to subtract 64 from both sides. That gives me 9. And then I'm going to take the square root, so I have p equals the square root of plus or minus the square root of 9, or p equals plus or minus 3. So that's what p equals, plus or minus 3, if our magnitude of our vector is the square root of 53. All right, last page. So I know that I have a vector a of -3, 2. I have another vector of 1, 4. I have another vector c of -2, -5. And I want to find vector a plus b. Well, vector a plus b is in component form. We have -3, 2 plus b, which is 1, 4. And then we just add our x values to get a new x value. That would be -2. And then 2 plus 4 gives us 6. So here in component form, we have our new vector. A plus b is the same thing as b plus a, so we would expect that if we add b plus a, we should still get -2, 6. B plus c, we're going to take b, which is 1, 4. We're going to add it to c, which is -2, -5. We're going to add the x values. That's going to give me 1 plus -2. That's going to give me -1. And 4 plus -5 gives me -1. So we're looking at our vector of -1, -1. Just jumping around, let's do the last one here. It's h. So we're taking b, which is 1, 4, plus a, which is -3, 2. That's an ugly 3. And then I'm going to add that to c, which is -2, -5. Now we're just going to add the components, so I have 1 plus -3, that gives me -2, and then -2 plus -2, sorry, 1 plus -3 is going to give me -2, plus -2 gives me -4. So I have -4, and then I have 4 plus 2, that gives me 6, 6 plus -5 gives me 1. So here is my new vector here. So continuing, looks like it's the same kind of problems. Up here we were adding, we're going to subtract. That shouldn't really be a big deal. We take q, -1, -5, and we're going to subtract our vector r, which is 3, -2. That gives me -1 minus 3, that gives me -4. And then -5 minus negative, that's a positive, so -5 plus 2 gives me -3. Or q, which is -1, -5, minus r, which is 3, -2, minus p, which is -4, 2. Just the components, -1 minus 3 gives me -4. -4 minus negative, that's a positive, 4 gives me 0. -5 minus -2, that's a positive, so -5 plus 2, that's -3. And then -3 minus 2 gives me -5. So we have our new vector here of 0, -5. So, yeah, that makes sense. All right, so we're going to continue. Number 3 says, consider that we have this vector a subset 1, a subset 2, and I want to show using vector addition that a plus a 0 vector equals a. So I'm going to take our a subset 1 plus a subset 2, and I'm going to add it to our vector of a 0 vector. And when we add these together, a subset 1 plus 0 gives me a subset 1, and a subset 2 plus 0 gives me a subset 2. So I just showed that when we add a 0 vector, we should end up with what we started with. Now, using vector subtraction, I'm going to show that a vector minus itself equals 0. So I have a subset 1 A subset 2 is our vector, and we're going to subtract A subset 1, A subset 2. A subset 1 minus A subset 1 is going to give me 0, and A subset 2 minus A subset 2 also gives me 0, so I have a 0 vector. All right, so continuing, we have here a vector P, which is 1, 5, vector Q, which is negative 2, 4, and vector R, which is negative 3, negative 1. And I want to find, oh, it looks like, I think that I actually don't remember, I think what it wanted us to do is find something like this. P plus Q, and I should say the magnitude of P plus Q. We'll also do the magnitude of Q minus R. You know, I didn't print this other page. It looks like I might have run out. I don't know. I'm not sure why it didn't print. So let's just do these two examples and then we'll be done. So I have vector P, which is 1, 5, plus vector Q, which is negative 2, 4, and I'm going to take the magnitude of both. So I'm going to add the components. That gives me 1 plus negative 2. That gives me negative 1. And I have 5 plus 4, which gives me 9. And we are going to find the magnitude of this new vector. So I have negative 1 squared plus 9 squared, all under the square root. That gives me my magnitude. Negative 1 squared is negative 1 times negative 1, which is 1. And 9 squared is 81, so I have plus 81. So we're looking at our new magnitude being 82. Sorry, the square root of 82. Now I don't know if this can break down into something more simple. It's 82 is even, so I'm thinking that it probably can. So 41, I can see that I think 41 is already prime, so we're basically done. So we just have the square root of 82. That is the magnitude. The magnitude of our new vector is the square root of 82. That's the size of our vector. Let's do the next one. We're finding the magnitude of our Q vector, which is negative 2, 4, and the magnitude, subtract that from our vector of R, which is negative 3, negative 1. Now we're going to add the components, or subtract in this case. That's going to give us negative 2 minus negative 3. That's a positive 3. So negative 2 plus 3 gives us 1. And 4 minus negative 1 is, again, it's positive. So 4 plus 1, that's 5. And we're going to find the magnitude of this new vector. So 1 squared plus 5 squared, all under the square root. That gives me the square root of 5 squared, which is 25, plus 1 is 26. So there you go. It's the size of our vector, or the magnitude of our vector, is the square root of 26 units. Great. I hope that was helpful, and have a wonderful night.